the formulation of quantum theory, modulo one thing. I didn't give you the rigorous treatment of infinite dimensions. Well, as rigorous as I can handle, at least. That's actually in the notes you have. So that, strictly speaking, should be in the formalism. But I didn't want to. I wanted to move on to other things. OK, so what I'm going to do is, here's what I suggest. We're done in this topic. Now, for part 2, we're going to look today at, entanglement is now recognized as an important resource for quantum information. It's an important feature of condensed matter systems. It's just an important concept. And so what I'm going to tell you about is the history of how we came to appreciate that via the story of non-locality, which is a topic of interest in and of itself. We're going to do that today, maybe also tomorrow, maybe half of tomorrow. Yes?
I'd like to do the tutorial on Bell's theorem. Will we know enough to do that?
Oh, well, I'm going to start. I'm doing it today.
Yeah, okay.
Yeah, okay. So today and maybe a little bit tomorrow, we'll discuss some of it. Maybe, I don't know, we'll see how fast it goes. Depends how many questions you guys have. There was a specific request to cover Poisson brackets, which is this kind of abstract formulation of quantum and classical theory. And you see this emergence of the difference based on whether the algebra is commutative or not. So I'll do that. That's not in the notes. This is in the notes. Now here you guys get to help me choose what to do with the remaining, say, 2 to 3 lectures, 2.5 lectures probably. No. This is going to take half a lecture. So 2 lectures. So what I'm going to ask you to do is consider these topics, and then maybe we'll take a vote, and then we'll cover what you want to see.
To some extent,
Huh?
Huebner functions.
You mean with Aggie?
Yeah, I think she did that.
You introduced the Wigner function. Great. No, I'm going to do something. I would do something. So basically, OK, let me tell you a bit about each topic, and you can help you decide what you wanted to see. OK, so this is some pretty advanced math for a physics crowd. So this involves a little bit of measure theory, convergence questions, infinite dimensional Hilbert space topics that are, I just kind of, to use Robin Blomkoot's expression, it's a topic where I'm kind of hanging on with my fingernails because there's kind of like always another question I don't know the answer to because this stuff just gets arbitrarily complex. But I can certainly give you a lecture on it and give you a sense of what you need to understand a rigorous formulation of infinite dimensions. Continuous outcome POBMs, that's in the notes. The infinite dimension stuff is in the notes as well. So one consideration you might have if you want to make my life a little bit busier is you can ask for a topic that's not in the notes, in which case I have to actually prepare the lecture. So this is in the notes. This is in the notes. This is not in the notes, but it would be my pleasure to prepare a lecture on it. So continuous outcome POBMs are basically that, exactly that. It's how to handle situations where you have a continuous outcomes are a continuous set. We've considered the discrete index case, K, labels our outcomes. To deal with the continuous case, we have to do a little bit of measure theory, which is probably healthy for you to see. A little bit of overlap with this. It's just something to see. Contextuality, we're going to see non-locality today. That's a special case of contextuality. My own research recently, we've had a result where we managed to connect. One of the big questions in quantum information is, what is it about quantum mechanics that makes quantum computers more powerful? And so we've provided a partial answer to that question by showing that the operations you have available to you, whether due to some restriction you impose by hand or you build a device and you can't reach the full, the whole reason we did the generalized postulates is because it's impossible in the lab to create the ideal pure states, the ideal unitary transformations, and so on. So we need a generalized description of the practical realizations of these things. That imposes constraints on what you can do in the lab. And given those constraints, you can ask, do I have enough operational capability to do something useful for quantum information? And what we showed is that you have to demonstrate contextuality as a necessary condition to achieve a quantum speedup, which means some kind of exponential advantage over a classical computer. So I won't give you that whole story, because that's packed with too much information. But at least we introduced the topic with contextuality, which I feel like we've recently kind of put back on the map. It's a 50-year-old concept, which we've kind of given new life to with this result. The other thing we can do is just cover topics in quantum information. I could tell you a bit about quantum teleportation, no cloning, things like that.
I think they'll cover that, like if they choose to do the quantum
This explorations course.
Yeah.
Well, I mean, you could see it as, I think that's true. They could certainly just take the quantum information course, but maybe some of the students are kind of undecided about what they want to focus on, and this would just be like one lecture giving you a flavor of the kinds of things quantum information is about, especially for the students that don't take it. They might want to just have a sense of it. And the other thing is Wigner functions and quasi-probability, which, Aggie already introduced you to Wigner functions. Actually, this contextuality result builds on the work my group has done with this topic for doing Wigner functions for finite dimensional systems. Here the idea is you try and cast our operational formulation of quantum theory as a probability theory. And you show that you see that you can't do that, but if you allow the probabilities to become signed measures, which means the probabilities can become negative, which is physically meaningless, then in the states, I mean, the operational probabilities are still positive, but this kind of intermediate tool you use is a Wigner function, and it has negative probability, and that's actually intimately related with contextuality in this particular scenario that we looked at. So there you have a sense of it. Maybe what I'll do is although there's one request for the Poisson bracket formulation, maybe I'll throw that in with these topics on this vote you're going to do. And I'll put an asterisk next to the things that are in the notes. Okay, that's it. Yeah. Okay, so let's do this. Oh, is there a question first?
Yeah. The Wigner function stuff, or possibly other things as well. What is related to like field theory? Because like seeing as we're going to kind of be going on to do all this, highbrow, high energy stuff in the future, maybe that would be of interest to people. Like, what do you think personally would be most useful for like, say, our other courses which involve quantum ideas?
Well, if you're going to do it in the other courses, then none of this would be.
Well,
there'd be no point in covering something you're going to see in another course, right? I mean, I guess unless you give me like the flavor of things. Look, I don't work in that setting, so I think that you can just pick up a textbook and get from that what I would tell you. But these topics are things that I've worked on in my research, well, except for infinite dimensions.
I mean, within these.
Oh, within these
I don't
topics.
mean like, yeah.
Oh, so within these topics, for those of you who are interested in the relativistic setting, I think maybe this is important because, I mean, it gives you some deeper understanding of where quantum mechanics comes from in an abstract theoretical setting, which is maybe relevant. Probably this also would be very useful because I know that the infinite dimensional stuff gets, if you're doing quantum theory on curved space-time, or if you're doing loop quantum gravity, the issues we're just going to touch on here actually go quite deep into in those fields. So I think maybe these two topics, this conceptually and this mathematically, would be a good kind of background lead-in to those areas. Any other questions? Yeah.
How many are we going to get a chance to do? And
Probably 2 or 3, maybe, depending on the topic.
so maybe we can vote for 2 or 3?
Yeah, okay, you can vote twice. All right, I'll leave. It's the honor system. You see your neighbor voting more than once, you have to nudge them with your elbow. All right, we'll start in order, okay? So how many votes for Poisson bracket? Oh, wow. Too many to count. All right, that's a check. How many votes for infinite dimensions? 8 counting. 1, 2, 3. All right. How many votes for continuous outcome POVMs? All right, good for you guys. How many votes for contextuality? Oh, wow. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 14, 15. How many votes for topics in quantum information? These numbers are all good to within plus or minus 2. Wigner functions and quasi-probability. All right, well, good. I love it when there's a majority. OK, great. So we have winners. And this one, I just put a check mark. All right, I'll try and squeeze it all in. I guess contextuality will be our, well, OK, I'll leave the infinite dimension stuff for last, because it's in the notes. So if you want to read it, you can just read it. All right, so I'll do today, tomorrow, Thursday, and then Friday. Hopefully we'll stay on schedule. Great. OK. So now let's talk about entanglement and non-locality. So this, to me, is one of the most intellectually exciting discoveries of physics in the 20th century. OK, let's just launch right into Bell's theorem. I'll give you the history afterwards, because I want to do some math first. OK, so here, we'll just launch right into Bell's theorem, which is the most important part of all of this. So now Bell's theorem is a theorem on data. It's a theorem about data under some constraints. There's nothing to do with quantum mechanics. Quantum mechanics just violates it. All right? So we imagine the following setup. We have a source. And that source sends invisible particles to detectors, which we'll call this detector Alice and this detector Bob, following our convention. So now Alice and Bob, remember Alice and Bob have a measurement detector here, so a measurement device here. So that means they have a knob. Each of them has a knob, and that knob involves choosing what measurement they're going to do. So Alice has a choice of measurement setting. And that choice is, they're just labels. So it's A, and A can be either A0 or A1. These are just two dial settings. Doesn't even matter what they are. All right, and then similarly, Bob can choose some value of B, which is his knob, B0, B1. And now, of course, their detector. So here, I'll draw Alice's detector. So here's her detector. She's receiving this particle coming from the source. And then she has her knob here, and that points to either A0 or A1. And then she also has a pointer. And that pointer outcome can point to one of two outcomes. X, which has two outcomes. The pointer is in the 0 position or the 1 position. And similarly, Bob. And then similarly, I'll draw them both. Here's Bob's detector. And he has choices B0 and B1. And then his pointer points to Y, which is an element of 0 or 1. And what we want to do is we want to label X and Y based on what the detector setting was. Okay? So Alice gets outcome X, and then we have to keep track of whether it was for A0 or A1. So in general, we want to write this as X of A sub I. And here we want to write this as Y of B sub K. Here, let me just change this I to a J, because that's what I'm using in my notes, and I want to be consistent. There was a question.
So those are discrete outcomes.
Yes.
So in the lecture notes, we have interval.
Excellent.
So that
Paying attention. Thank you. Yes. OK, so let's do that. Let's make this an interval. The pointer can take on a continuum of values. The theorem works in either case. I hope my derivation. So I think the derivation is slightly different if you consider the continuous outcome case. But well, we'll find out which one I did in a moment, won't we? All right. Anything else? No, we're good. OK, good. So now what do they do? So I can't promise that the figures have the same notation as the notes. So this is a draft, of course, what you have in your hands. So please do let me know if you see typos and so on, or have any other suggestions. So now what happens is, at the source, of course, we have our Go button on the source. So we press Go. And then some moment later, these lights light up. And then we get our outcomes. And then we repeat, right? So we repeat the experiment, repeat experiment many times. Alice and Bob make random choices, make random independent choices for the measurement settings. For A sub j and B sub k in each repetition. Okay, and then what we're going to do is we're going to consider the statistical average of the results. Okay, combining repetitions, we can compute S, which is defined as the expectation of A0, B0 plus the expectation of A0, B1 plus A1, B0. And then we throw in a minus sign for convenience. I mean, we can construct anything we want. We can compute whatever we want. And it turns out this is a good choice of something to compute because we'll see something interesting.
I'm a little confused about the pointer positions and the measurement settings. Shouldn't is it the measurement settings that are supposed to be a continuous set? Because
No.
No? And the outcomes can be continuous?
Mm-hmm. Think of it as, OK, the reason why you want to consider, I mean, quantum mechanically, there's discrete outcomes.
Right.
But remember, we're just writing down some structure which quantum mechanics will violate. But the idea is, suppose I'm doing this classically in the following way. I have some sphere. Suppose I have a pair of classical spins.
Mm-hmm.
So classical tops.
Mm-hmm.
And the classical tops are going to have zero angular momentum.
Mm-hmm.
But each one has some angular momentum in some direction.
Mm-hmm.
But they have to add, they're back to back. So
Right.
they have to add the zero. Okay?
Right.
And then what would happen is I send a top to both of Alice and Bob. And then what Alice and Bob do is their measurement is what's the projection of the angular momentum along an axis. So B0 and B1 would be two choices. I'm going to measure along the z-axis, or I'm going to measure along the x-axis. So here, Alice and Bob independently choose which axis to measure.
Okay.
And now suppose they were for simplicity, let's say they're back-to-back along the z-axis. Then if Bob measures along z, he's going to get exactly +1, which is the maximum value. And Alice, say she measures at 45 degrees. Okay, so she's going to get minus 1/√2. So that's why it's a continuous one, because the angle is a continuous angle. So you can get an arbitrary number between, where here 1 and -1 are the renormalization of, oh, I'm calling it 0 and 1. Actually, yeah, so this is -1 to 1 in the notes, so let's do it that way. I mean, this is just some, I mean, the point is there's some interval. Sorry for that mistake, but you guys should have caught that. You all have it right in front of you.
That might have been part of why I was confused, because I thought they were supposed to be like quantum spin up, spin down.
All right, good. Okay, good. But okay, so that's clear? All right, so what do I do with this? Is this like I just try my best and we see what happens? Okay, so what does that expectation over there mean? Well, as you see, it means ALBK is equal to the limit as n goes to infinity, where n is number of repetitions, of this correlation. It's just a correlation function. So here the index indicates which run we're talking about. Here x is the outcome we got, conditioned on the setting. Isn't this called J? Am I calling this J or L? What's my, let's call it J. So it should be J over here. All right. It's just a dummy index, so it doesn't matter. Okay, I don't know why I say this right away, but just as a forward reference. So, okay, so as I just mentioned in response to a question, we could perform this experiment with classical tops. By tops, I mean in angular momenta. Satisfying. Okay, here I'm going off script, as you notice. What do they satisfy? We want the angular momentum of the first particle plus the angular momentum of the second particle to be 0. Is that the right condition? And then the measurement outcome, something like the measurement outcome, say x, conditioned on aj, would be equal to some unit vector n along some direction j times j1. And this, and then divided by the magnitude of j, and this should give us a number that's in the interval -1 to 1. Okay, I think that's right. Let me know if that's wrong. I'm just writing out mathematically what I said in words, so let's make sure that I didn't miss anything there. And similarly for y. So quantum mechanically, we can perform, yes?
I'm just wondering about the formula you bring down there. I'm just trying to get my head around it. So this is kind of just making the assumption that there is, like, even though we're only ever measuring like 1x for the part, like for our, for each time we do the experiment, we're measuring one of the x objects. We're assuming that all of them exist, like independent. That's the whole idea.
I'm assuming you have a pointer position in the experiment. That's all I'm assuming.
But like for each AJ, independent of whether or not, like, so when we do this experiment, we're explicitly setting our pointer to just 1A.
You're not setting the pointer. The pointer goes based on the
You're
input.
picking what you're measuring.
You pick, okay, so Alice controls this, and she observes the pointer. So her choice affects the knob. She doesn't move the pointer.
Yeah. So, because not in every experiment you're not measuring all of these, but we're only taking the ones where you are measuring.
No, in every run, Alice has to make an independent random choice. How she does that is a very subtle issue. But, well, it's not subtle. It becomes subtle. The conclusion of this theorem is so dramatic that the assumptions have been scrutinized to death because people don't like the conclusion. So, I mean, and the experimental tests, it's been experimentally tested to death because people don't like the conclusion. So, but I mean, if you accept the conclusion, then it's just an experiment like any other, and it doesn't need to be subjected to this, these insane. Well, I shouldn't say insane. I should be a little more careful. This is recorded, right? But these rather esoteric critiques. Okay, good. So let's move on. So quantum mechanically, we can do this experiment with two spin-half particles. Now this is where the discreteness comes in, because quantum outcomes are discrete. Unless you do a continuous outcome POVM, which you'll never know about. Well, not from me, at least. Or unless you read the notes. OK, quantum mechanics is two spin-half particles. And then what you would have is this mathematical concept would be realized in the following way. It would be, remember our postulate 2. We would have the trace of the preparation rho against the quantum spin operator along. OK, I went off script here. Let me change my notation here. Let me change n to a. So a is a unit vector. Okay, so now. Okay, so now also for those of you who get thrown off by notation, here the hat means unit vector. So here a hat is a unit vector. Maybe I should have just stuck with n. But in my notes, I have a as a unit vector, so let's just do that. Tensor product. Now, normally you would see this written out without the tensor product, because people just suppress the tensor product symbol normally. But I'm making it explicit. So this is our observable, and this is our preparation. Okay, so we can do this experiment, and in this case, what are we going to get? Well, in this case, remember, spin outcomes are either up or down. There's no in between. So either you're going to get plus a half or minus a half. Well, we can just divide by a half and call the outcome +1 or -1. So the quantum outcomes are either going to be +1 or -1, or multiplying them together, which means the composite expectation is an average over pluses and -1s. But classically, we can have a continuous outcome set. Of course, classically, I can just do this measurement and then just say, well, if the result is in the positive, is a positive number, I just call that +1. If the result is a negative number, I call that -1, just relabeling. And that way we can compare directly with the quantum results. OK, so far so good. Now we get to the dramatic part. Now, I'm not going to give you Bell's theorem. I'm going to give you the CHSH inequality, which is better. It's an improvement on Bell. The derivation is simpler, and it makes one fewer assumption, which I'll get to later. CHSH inequality is the following. This quantity S is bound by 2 and -2. So here S okay, I've got to unpack this for you. What is happening here? Oh, okay. Well, for crying out loud, this is J and K, isn't it? Okay, so what's this quantity S? So we defined S operationally over there. That's how you measure it in the lab, okay? But now what we're going to have is two different models. We have the quantum mechanical model, which tells us how to predict the experimental quantity. And we're going to have a classical model. Take the word classical with a grain of salt there. We're going to have another model based on some reasonable assumptions, which is going to make a prediction for S. And so the idea is we have three things here. We have the experimental quantity, which I've defined S as. We have the quantum mechanical quantity. And we have this quantity from this model. And the whole point, the way this argument goes, is we're going to say this model makes very reasonable assumptions about the world. And it implies this constraint. And then we do the experiment, and we violate this constraint if we do the experiment right, if we do the experiment with quantum mechanical objects. And that, of course, matches the quantum mechanical prediction. Yeah. Yeah, this is where I have to give you the proper meaning of this, I have to tell you what is this model. Okay? So CHN is based on a model. So I should put it based on a model. And now let's look, what is the model? Yes.
Yeah, sorry. I have a question about the S. The first time you wrote the S, the minus sign.
Mm-hmm.
No, on this.
So here I just rewrote S in a different way, except I have a lambda here. So I can also write this as, I can remove the lambda and write this same expression again. So here, if J and K are both 1, we get the minus sign.
Yeah, I'm just asking why we have that particular minus sign.
Oh, it's just a choice that gives interesting results.
Okay.
So there's lots of choices of combinations of these things where we don't see a conflict. But this is a choice where we do see a conflict.
Okay. And S down here, where you have the continuous case where you've written down the integral, that's the lambda, rho of lambda, and the last S of lambda.
This is S of lambda, sorry. So, okay, well, let me just, okay, that was just a handwriting issue. Okay,
And that
good.
S of lambda is the same as the one over.
No. S is the same as that. S is obtained from S of lambda by averaging over the hidden variables. Okay, well, this is what I have to kind of explain now. What are the assumptions? So we assume that, okay, here I want to have the wording careful because we assume that there exist physical properties for a physical system. Okay, this is a realism assumption. So we call these, here we let, in particular, we're going to let lambda, which is an element of a set, so it can take on different values, denote the physical properties. okay, what does this mean? So if I'm talking about the story where we have two back-to-back angular momenta, those angular momenta are some spinning tops. We would write down the classical canonical coordinates for that system. Okay, so if I had a baseball, the position and the momentum are my canonical coordinates. If it's rotating, I guess then the angular momentum is implied by those. The point is we have physical properties which are, classically, these would be the canonical variables. For example, canonical variables. But we're not going to assume anything about the structure of classical theory here. We're just going to say that there are some properties. And if the world was obeying Hamilton's equations of motion, and those properties, the primitives would be the canonical variables. So in any given run, in any given repetition, the source fixes the physical properties lambda of the pair of systems. Okay? So lambda encodes exactly the physical properties the system was given. Yeah?
This is just a cross-reference between stuff I read written by Bell. Is lambda what Bell calls viewable?
Yes. Yes. So here, okay? So yes, so lambda would be called a viewable or a hidden variable. The word hidden variable is a bit loaded, so it suggests things that it shouldn't suggest. So viewable is good. Okay, we allow for the possibility that in each repetition, the lambda can change from time to time, right? Yeah.
What's viewable?
It's the physical properties of the system.
Okay.
It's a different word for exactly what I wrote. Okay, so we allow for the possibility that lambda varies from run to run. Possibility that lambda varies from run to run. And so we assign a probability density to describe the set of possibilities. We're not saying what it is, we're just saying we can write down some probability density for these different values. Now, for those of you who know anything about measure theory, you'll notice that this is already an assumption because it turns out that in physics we use probability density functions. But generally, if you have a set and you have some probability theory on that set, you have measures. And it's only a special case when the measure can be expressed in terms of probability density. It's when that measure is absolutely continuous. So now the examples of measures that are not absolutely continuous are these very, very esoteric things that don't happen in the real world, as far as we know. So it's a mathematical nuance. I very much doubt it's relevant, but it's important to keep in mind. So this is, and people don't really identify this as assumption, but I think it is. But anyways, whatever. I can't say more about that because I don't know that that's been explored carefully. And I doubt that it matters. OK, what else?
Sorry, 2 questions, Jerry.
Yeah.
Firstly, so the assumption you've written down is like the hidden variable assumption. There's no locality yet, right?
We haven't imposed locality yet.
Second question is, is assuming that the physical properties are set by the source, like the same as assuming they exist at all, or do we have to assume they're set by the source when we assume they exist?
You know, I mean, this is just my wording off the top of my head.
Right.
I wouldn't scrutinize it too carefully. I think that's something you can think about later. So hence, because of this setup, we have the following. We have that the expectation of AJ bk is equal to integral over d lambda. So this is where we're assuming that the measure on the values of lambda is absolutely continuous. So we can write this down in terms of probability density. That's something people don't worry about. So don't worry about it unless you're really obsessed with this topic. Okay, so now what's happening here? So all we're doing, first of all, we're saying this is an average over runs on the left-hand side. And I'm saying, well, that lambdas were created or established with some variation, and that variation then has to come into our statistical average. And then let's look at what's happening here. Here we're saying, remember, x and y are the outcomes. X and y are the outcomes for Alice and Bob. And those were outcomes, remember, they were conditioned by the setting. Well, here I've put the setting inside the probability. So I'm saying that here's why CHSH is a cleaner theorem than Bell's. Because CHSH allow the possibility that the outcome is not determined by the measurement setting and lambda, that it's only probabilistic. So it allows for, Bell had assumed determinism. He assumed that the outcome was determined by the settings and the hidden variable. But they said, actually, we don't even need that assumption. We can just allow for a statistical or probabilistic effect. So here just is saying that there's some probability of getting the combination x, y, 1, 1, 0, 0, 0, 1, or 1, 0. And that's conditioned on the settings and the physical properties. So that's all that's saying. This is like standard probability theory.
So apart from having the probability density, so apart from having the probability density depending on lambda, we're also having like another probability distribution on the outcomes of x and y depending on the lambda. Okay.
So we're trying to make this as weak as possible. So I mean, in Bell's original derivation, he just had x and y being a function of a, b, and lambda, but now we're weakening it to a probabilistic dependence. Okay, so far we can't derive a contradiction. So what have we done here? So basically, so far we've assumed realism. They're just our physical properties. Now, I want to make a comment here, which is confusing for a lot of people. We haven't assumed hidden variables. Okay, so far what I've done, you could just say, let's assume that lambda is the wave function itself. All right, so for those of you who want to think the wave function is physical, at your own risk, you can fit that into this model. Okay, you can just say lambda is the quantum state, right? That's the physical object I'm dealing with. And then this probability density function would be some Dirac delta function. So here, I'd integrate over all states in the Hilbert space. This becomes a Dirac delta function, which picks out the particular state I prepared at the source. And then this is just saying that now there's some probability of getting outcome x. This is just Born's rule, basically. Okay, so we haven't assumed hidden variables. We've just assumed that there's something that's physical. That could be the quantum state, could be something else. Yes?
On the right hand side of the probability density is like AL is the AL and BK are the things you're measuring, and lambda is the state that's going in what you just described. Right?
Yeah, so in that
X,
picture,
X and Y are the things. Well,
X and Y are the outcomes you get.
Yep.
AL and BK are what observable are you measuring.
And yeah, right.
And lambda would be either the wave function,
Yep.
so this would be the Born's rule.
Yep.
So the probability of getting some outcome, and then and this is just what we're measuring is x, y. What's the outcome we got, the product of the outcomes. Okay, so the point is, this includes the possibility, that lambda is equal to some projector, and capital lambda is equal to the Hilbert space, but more precisely the complex projective space. Probably shouldn't have done it in a fancy notation. I should have just called this a vector, and I should have called that the Hilbert space. But maybe you guys are comfortable with, maybe you're not. Anyways, that's all I'm saying. Okay, so now so far everything's pretty innocent, and we don't have a contradiction with experiment yet. Now the last step we do is we assume the locality. So next we assume locality. Okay, this involves two assumptions. One is what's called parameter independence. So what I want to say is now I want to say that for whatever reason, I feel comfortable with the following assumption. I feel comfortable saying that whatever outcome Alice is going to get, it can depend on her knob setting, and it can depend on the properties of the source, because that's in her backwards light cone. But it cannot depend on what Bob chooses to do, because Bob is really far away from her. Now, how do we motivate that? Well, we can say, look, I've taken away their cell phones, and I put them in electromagnetically shielded cages. And so I'm confident that whatever Bob does, no one's going to know what's happening inside his box, okay? And similarly for Alice.
Can't you just separate them far enough that they speed of light thing?
And that's exactly the other way to do it, is to say, well, look, we could also say, let's justify this via light cones. So we can say, look, do it this way. Here's Bob's detector, and here's his backwards light cone. And here's Alice's detector, and here's her backwards light cone. And we put the source here. Okay, and then the particles come into Alice and Bob's detectors. And we force Alice and Bob to choose their settings after some line which is beyond their light cones, right? So this is backward light cones. Now this is time is going this way, right? So this is space, and this is time. So now if Bob goes and we're preparing the source at time t equals 0, and say it takes time tau to reach the detectors. Now if Bob just sets his detector setting when his detector is back here in time, at time t equals 0, then he might be inside Alice's light cone. So then we could say, okay, there's a causal influence from Bob's detector setting to Alice's outcome. There's the possibility. But what we do is we force them to choose their measurement settings just before the particles arrive. So now the choice here can be some random process. It can be some random quantum event. It can be Alice and Bob's free will, whatever. It just has to be independent. So what's parameter independence? We say the probability of outcome x, or alternatively y, does not depend on the random choice of remote setting. And for X, it would be B or A. Okay, so I'm just writing two sentences in one here. Read this sentence, ignore the parenthesis, and then read it again, ignoring the term before the parenthesis. So this says, the probability of outcome X at Alice's detector does not depend on the random choice of remote setting B at Bob's detector. And similarly for Y and A. That's pretty much all I'm going to get out of this board, right? Is there one more level? Oh, yeah. Middle. Oh. Yes. And then assumption 2 is outcome independence. And that's the assumption that given the physical properties of the systems, the conditional probability of X does not depend on the remote measurement outcome. Oh, I didn't write down mathematically. Hold on a second. I forgot something over there. So this is the statement mathematically. What this means is the probability of X, which in principle could depend on A, lambda, and Y. X could depend on the outcome Bob got. But we're saying, no, that can't happen because we're making sure it doesn't happen via some method like space-like separation. So we're insisting that we have the following. Y can't influence the probability of outcome X. And similarly for Y, and I should have written over here, the probability of X conditioned on both detector settings and the physical properties and the outcome actually doesn't depend on the remote setting. So it doesn't depend on B. So then these two assumptions imply factorization. Which is that the joint probability of X and Y conditioned on A, B, and lambda is equal to a product that the probability of X depends only on Alice's detector setting and the properties of the physical system, and the probability of outcome Y depends only on Bob's setting and the properties of the physical system due to the preparation. Alternately, you can just directly assume this and not worry about assumptions 1 and 2. You can just say, okay, well, this is reasonable. Or you can go back and justify it from assumptions 1 and 2. So this is the locality assumption. Locality condition. Yes?
The main reason why this is going to fail is because I prepare like a single stated up, down, cross, down, up. Don't ruin the surprise. But my question is, like, if I was to do this for two tops, as you described before, and I set them up so that they both have, say, opposite angle dimension, but the idea is like the individual angular dimensions of the two tops are contained within lambda, so it's not.
Yeah, lambda is the information about both tops.
So it doesn't.
But lambda does not include information about Bob's detector setting.
Yeah, but like Y is no longer doesn't for X, even
Sorry?
Y doesn't need to be dependent on X.
Is that a question, or you're just asking me to
I'm
confirm?
going to confirm it.
Yeah. Okay, we're good?
We can't hear anything from back here, so
Oh, sorry.
Yeah,
It's probably
that would
better.
be very useful.
That's pretty.
Ouch! All right.
What's going on? It's funny about
Okay, so now we apply this. We apply this assumption
There it goes. Listen up with one more.
to our main quantity of interest. And we get the sum over xy of xy, probability of x a j lambda times the probability of y b k lambda, which in particular means that we have ai lambda, aj lambda, bk lambda. Tell me how to define these things. Good. Where aj lambda is equal to a sum over x. So it's just a local quantity. I guess this should be aj on the side here. Why am I? Yeah, okay, good. All right, so those are our assumptions. And this is the consequence of the assumptions. I wrote this over here, right? Oh, here I have xy in parentheses, which looks a bit weird. So let me remove the parentheses. So essentially, we took this formula. Okay, so I'm going back and forth here. We can write this as, this is what I'm missing, I think. This would be aj bk subscript lambda. So that's assuming that lambda was fixed, but then we're allowing the variation of lambda. And so when the bracket without the subscript lambda means we've averaged over different values of the possibility of variation in the set of lambda. Yes, in the back.
You want an X maybe on that
Yeah, it looks like lambda.
bottom guy there?
Oh, thank you.
Looks like lambda.
Like multiplied by n.
And I should have an x in here too, right?
Yeah.
That's what I mean. Yeah, you should be multiplied by next there. Yeah.
Yeah, so that's a typo in the notes. So I'll have to remember to fix that.
What page is it?
Page 6. Oh, sorry. It's not page 6 for you. It's page 6 for me. 42. I was waiting where the back one last is one. Oh boy. All right. Okay, so now the rest is just math. Okay, so basically we have S of lambda is equal to A0, B0 plus A0, B1 plus A1, B0 minus A1, B1. Remember, I have to take a picture of that because I won't remember what I agreed to lecture on if I don't. Okay.
It's online.
Sorry?
It's online.
All right, good. All right, so now we have each of these quantities. A sub I is in the interval -1 to +1. Okay, good. So I did the derivation in general. So then we can rewrite this as here's the nice little trick. You just rewrite it as A0 times B0 plus B1 plus A1 times B0 minus B1. And then we can deduce that this is less than or equal to B0 plus B1 plus, amazingly, this inequality is tight. Doesn't look like it would be, but. So what happened here? Well, look, this is a number between 1 and minus 1. How does this work? Let me remember how this works. Why do we know this is true? So we say the average value of the outcome x given measurement of A0 is some number between 1 and minus 1. So the biggest this can be is plus 1. And the biggest this can be is plus 1. So let's assume they're both at their largest values, and then write this as an inequality. So this is less than or equal to just the size of this term plus the size of that term. Okay, that's simple enough. And then now, B0 and B1, we can assume one of them is bigger than the other. And once you've chosen that, I can just call that one B0. So then without loss of generality, we'll just assume that B0 refers to the larger result. B0 is greater than B1. Which means that S of lambda is less than or equal to 2 times the expectation of B0. But the expectation of B0, the magnitude of that is at most 1. So this is less than or equal to 2. And by a symmetrical argument, we can deduce the lower bound. I can't remember now if that symmetrical argument is actually assuming that B1 is less than B0. I'd have to think about it. But anyways, I'm sure it's easy to see that we have the lower bound of minus 2. And now we average over lambda. If for any given run, this particular funny linear combination we're looking at is bounded by 2, then the average is bounded by 2. And then we get that S itself, which is the average over S lambdas, has to be between 2 and minus 2. So that all sounds pretty fine. Nothing wrong with that so far. But then here's the shocking part. Quantum mechanics predicts a violation of this inequality, which means that one of our assumptions is false about the world. So we did this very plausible derivation. We used some very basic mathematics, some basic geometric inequalities. We snuck in a little assumption about the measure being absolutely continuous, so we can write it as a probability density function, which I don't remember anyone ever mentioning, but it's certainly true. That's an assumption. And we get something that's contradicted by quantum mechanics.
I think even if that's a measure, then you show us that lambda, right? Not the S. And so if that row, if like you rewrite it something below d mu when you were some measure, and you got like S of mu.
Yeah, you're right. I mean, I'm pretty confident it's completely. I'm sure one can do this more carefully without assuming absolutely continuous things. It would just be mathematically a bit more messy.
Yeah.
So quantum mechanically, and I think this would be a good exercise for them to just derive this. Quantum mechanically, ALBK is equal to, sorry, quantum mechanically is equal to sigma dot A tensor sigma dot B. And we can just assume there's a pure state preparation. Let rho be some pure state psi. And we get psi equals sigma dot A tensor sigma dot B psi. And now let's say we consider a particular preparation which is not a product preparation, but an entangled preparation. Consider psi equal to psi minus, which is the singlet, which is equal to 0, what is it again? 0, 1 minus 1, 0. Well, I'll do it in the spin language. Spin down, spin up, which is the definition of psi minus, minus spin up, spin down over square root of 2. This state is so important, it has its own symbol, capital psi minus. And then what you find is, and this is, so here's an exercise. Show that the expectation of, in psi minus, of sigma dot A tensor sigma dot B is equal to minus A dot B. Now remember, A and B are unit vectors. Remember, A and B are unit vectors, which correspond to a direction in space. Now here we have a particle propagating towards the detector with some spin. We're going to do a measurement in the plane perpendicular to the, say, the propagation. We're measuring spin in some plane. So far, so good. Now what we do is we choose the prior possible settings, A0, A1, B0, and B1, according to the following choices. So this is the x-axis, this is the y-axis, and this is 45 degrees. That's B0, and this is B1. And then what we get is that S is equal to 2 times the square root of 2, which violates the CHSH inequality. Now, of course, you see something like this and you want to do an experiment right away. So this experiment has been done many times. Alain Aspect did the most decisive demonstration, the first decisive demonstration in the early 80s. And it confirmed a violation of the CHS inequality. So he managed to create an entangled state of two photon polarizations using down conversion or something. It creates an entangled state of the two polarizations. And then he measured the photon polarization at two space-like separated detector locations with random choices of measurement. He constructed this linear combination that we chose. And he found S, well, I don't have the numbers with me, but it was within statistical error, it was greater than 2. And it sure as heck better be less than 2 root 2, or else you're violating quantum mechanics. So it confirmed the quantum mechanical prediction. So experiment agrees with the quantum prediction. And so we have overwhelming evidence that one of these assumptions is false. And the question is which one? Generally speaking, people assume that the correct interpretation of this is that the assumption of local realism is what's at fault, is what the problem is, which means we either have to abandon the very notion of physical properties existing, or we can keep that notion but allow those to have those physical properties to be influenced in a non-local way, which violates the spirit but not the letter of special relativity. So an important point here is we can't use these correlations to signal faster than light, because Alice and Bob have no control over what outcome they will get. All they know is that when they come back together and look at their outcomes and construct this statistical quantity S, they see that they can't explain it via local realistic properties. But they can't use it to communicate. And that's something you have to think about quite a bit. A bad analogy, I don't think this is a very good metaphor, but it gives you the spirit of how you can have something that's non-local but no signaling. And this is from some popular science writer I read when I was like 12 or something. But the idea is you can think of it as like, suppose you have 2 decks of cards. And normally if I draw a card from a deck at random, I just get a random card, right? And I don't know what I'm going to get. Now suppose we have a special deck that we bought at a special magic shop, and then Aggie goes to Australia on vacation, and I'm here, and we decide, okay, at exactly like 3 p.m. Eastern time on a particular day, draw a card. And we'll both draw a card. And we'll both get a random card, but it will be the same card. Now, I can't use that to convey information, like if you get the 3 of spades, that means that I'm sending you this message, because I can't control what outcome she's going to get. All we're going to know is that when we get back together and say, well, what card did you draw? It's going to be like, oh, we got the same card. That's really weird. If we did it once, that'd be just weird. If we did it many, many times, it would be very weird. That's what Bell's theorem is. Very weird. Questions?
Just a typo in the notes, so it's figure 3 instead of figure 6.
Oh, thanks. Nothing. Wow, you guys are hungry. Okay, great. We can come back to this tomorrow and spend a little time on it. There's certainly the historical overview and some of the things I want to say. Yeah.
Yeah, well, I had a question about the significance of this lambda. So I think, as far as I understood, we are measuring some physical property. Say lambda would be the spin, and then we can make the measurement in some basis, which would be the A's and B's.
Lambda is an abstraction. We don't know what lambda is. It's just we're saying let's assume that there are physical properties. So we have a physical system, the spin, and then, yeah, so lambda would be, for example, let's suppose that the spin has some orientation in space. So then lambda would be theta and phi with respect to some axis system. That's all. So, okay, so yeah, in that example, if we think about spin in a very classical way, lambda would be some theta and phi with respect to some pre-established reference frame.
Okay, thank you.
And then so Alice, if the tops are correlated, then Alice would have theta phi and Bob would have theta prime and phi prime, which satisfy a constraint based on the Lang momentum. Okay, see you tomorrow.